Okay, well, we're going to convert, well, when we want to try to graph a quadratic function that's in standard form, it's not advantageous to, we know the x-intercept automatically, but it's not advantageous for us to go directly from that form to produce a t-chart to produce a graph. What we have to do is conversion. We've got to take it in standard form and convert it to either factored form or vertex form. The easiest way for us to understand this is to use an area model. We use an area model in terms of a rectangle. So we should all remember that to find the area of a rectangle, it's always equal to the length of the rectangle times the width of the rectangle. Now, if we think of it this way, then if you think about a quadratic in factored form. The quadratic in factored form takes the form x minus p times x minus q, and it often will have a multiplier in the front. We'll call it a. But what's going on here is you've got a times sign in the middle. So we can easily relate every quadratic function that's in factored form to a rectangle of a length, which we could refer to as x minus p, and a width, which we could think of as x minus q. Vertex form, if we think about how that's constructed, it looks like x minus h squared plus k. This doesn't quite look like length times width, but what if I manipulated it just a little bit? It's got that x minus h squared, which we know is x minus h times x minus h plus k. So once again, I see something here that looks like the length times the width, which does relate to the area of a rectangle, but it's got something added to it or subtracted from it. So I'm taking the area of a rectangle, but I'm adding some quantity to it, or I'm subtracting some quantity to it. So, and this will make a little more sense when we go through the examples of converting. But before you do your conversion, it's really important that you understand this area model. So let's look at a few examples of just building. The area model is composed of pieces. So this piece we let refer to as an x by x piece. It has a length of x and it has a width of x. So it's a square. We don't know how big it is. That's why we put x on it. So it could work with any quadratic function or any rectangle, any square. So it has an area then of x squared. So it's always going to represent your quadratic term. Now let's say I bring in this to the side. This guy, if you think about how he is built, he has the same length as the square, correct? So this side is x. This side we say has a unit length of 1, represents 1 unit. So this guy then would have an area, just that one piece, of 1 times x, which is x. He represents your linear terms that are part of a quadratic. And if I think of what I've done to my original figure, I've taken what was a square and I've extended it by 1 unit. So now this area model has a length of x plus 1 and a width of x. And we can get a lot from that. Let's just look here. If I looked at this area model, let's give 2 representations for it. Number 1, I can look on the inside because area is composed of the inside portions. That's what area means. The measurement is what is inside a figure. So looking inside my figure here, I can see that the area could be represented by me saying this piece that's x squared plus this piece that has an area of x. But I also know, so this portion, what I just wrote, would represent the area of the rectangle, looking at the inside. But I also know that the area of any rectangle can be represented by the length of the rectangle times the width of the rectangle. So if I look at the length is always my longer portion. This rectangle has a width of x and a length of x plus 1. So I could say x plus 1, which represents my length, times x. So we've given two different representations for what this model shows. We've given the inside representation, which is x squared plus x. We've given the length times width representation, which is x plus 1 times x. Now let's build another one. Let's say here, let me just delete this. Let's say here that I'm going to let you give me two representations for what I'm building. And for right now, I'm just going to be extending sides, okay? I'm just going to make my sides longer, not going to make them shorter. Because I can extend sides either way I want to. Now, this doesn't represent a rectangle yet, so I have to bring in these units that we hadn't talked about already. But let's think about what their dimensions in their area would be. It doesn't have a side of x. It's got a side of length 1, and this one is also a length 1. So this guy represents an area of 1. He's a 1 by 1 square. And I have to use him to fill in my figure, or else it's not a rectangle. It would be a weird shape, a concave polygon. All right, we already said that these rectangles, remember this guy, my starting piece is x by x. So he has an area of x squared. This rectangular portion has a length of x, and it's got a width of 1. So he has an area of 1 times x, which is 1x. Now these guys are the same way. Just because they're horizontal doesn't mean they're any different. So he has a length of x, and he has a width of 1. So he has an area of 1x. Okay. So let's give two representations. We'll start with the inside area of the rectangle. We'll use that definition that we wrote down in the beginning. The area of the rectangle is composed of all its pieces. So let's start with our quadratic term. I have 1x squared box plus, how many 1x boxes do I have? 1x, 2x, 3x, 4x. So that's 4x. And then how many 1 by 1s do I have? I have 1, 2, 3. Plus 3. And now give me the other representation of that same rectangle, which would be the length of the rectangle times the width of the rectangle. Remember, length is my longer one, so this side was x, which I extended by 3 units. So that would be x plus 3. And this side here is x units, which I extended by 1. So that would be x plus 1. Okay, so in terms of area, we're taking the area on the inside and writing it as a length times width expression, and we know that these must be equal because that's the definition of area. In relation to quadratics, what we're seeing here is that the portion that it shows the inside area represents my standard form of the quadratic function. And this portion represents my factored form because we're able to write it as the product of the length and the width, which is what factored form looks like, okay? So this is how we're able to convert between standard and factored form. Now, sometimes you're not going to be extending portions of sides. Sometimes you're going to be decreasing the portion of those sides. We can use colors to denote, like a different color. A lot of times we'll use green to represent an extension of a side, and we'll use red to denote a decrease in a side. But what I typically do is just do shading. So let's say I had this picture and I shaded, I'll just use my highlighter here. That doesn't show up very well, does it? Let's try this color. Yeah. I shade these boxes. What I'm symbolizing to you is that by these boxes, you can just shade them with your pencil. Instead of extending it by 3, I am decreasing it by 3. That's what my shaded boxes indicate. Let me go back to my regular pen here. So this would symbolize a decrease in that side of 3 units. That was X by X. And this one, since I didn't shade it, would symbolize an increase of 2. Now, I haven't completed my area model because it doesn't look like a rectangle. So I need to fill it in with my 1 by 1 units. And in this case, they're not 1 by 1 units. They're negative 1 by 1 units because that width was decreased, making it smaller. So each of these symbolize a minus 1 length. So all of these boxes, these red boxes, would also have to be shaded because they have been decreased by that. So building my area model, this guy was x squared. This is 2x. These are not going to show up, so let me write it up here. Negative 3x. These are shaded, so they're negatives, and there's 6 of them, so that represents negative 6. So the area being built together would be x squared plus 2x minus 3x minus 6. Now I need to combine those terms in the middle, my linear terms. So it's really, I had positive 2x boxes and I had negative 3x boxes. So that just makes negative x boxes. And I'm not going to write plus negative. Let me fix that. I'm going to write minus. That's the same thing. X squared minus x minus 6. Okay? Give me the length times width representation. Actually, we could just do it down here. This side, my length, is x plus 2. This side is x minus 3. Okay? So I know that the quantity x squared minus x minus 6 would be equal to the representation x plus 2, x minus 3. And I can think of this as the standard form equation that is the same in a different form known as its factored form. Okay? And that is understanding your area model. Now you're ready to convert to factored form.